Hey, everybody.
Hello.
Hello, hello. Let's see here. We have Catherine, we have Leo, Tyler, Sue, Hector, William, Kenya, Romel, and Kevin, and me. That's awesome. Great. So I'm going to go over quickly a sort of an abbreviated version of this experiment. I'm going to give you some data so you all can do it. And oh my goodness, let's see. I've got having a little bit of trouble getting the getting it all together here, but it's coming. Let's see. Let's see. So we're going to do some analysis of a mixture of organic solvents, and that's going to be acetone, ethyl acetate, and toluene. And what we're going to do is we're going to figure out how much of each of those three components is in a mixture. And we're going to do it in 3 different ways. So first of all, let me get us some data to work with here. Let's see here. I just got to look at some of these that are coming up here. Shucks. Going through the archives here. Alrighty. So what we did was I gave everybody in the class standards of acetone, ethyl acetate, and toluene, and an unknown mixture of these three, right? And we have the, we have the approximate composition. That's not a problem. And then what was done was a standard dilution of these three was made, and then the absorption spectrum was measured. And then the same standard dilution was made using the unknown mixture. And let us see here. Let's just sort of get this data together, and then we can go through it. Hi, Dios. Let's see here. So first thing we want to do is we want to save these data in our folder here. As XLSX files, and we'll let this be Calvin ABC UVBiz.xlsx. And so now any changes we make will be saved properly here. Now we have a wavelength, absorbance, wavelength, absorbance, wavelength, absorbance, wavelength, and absorbance, right? We actually only need one wavelength column because these are all the same length and all of the wavelengths are identical. So what I'm going to do is I'm going to move these labels on top to the right one click so that they correspond to the absorbance of that species. And then I'll delete the wavelength columns. And now what I'd like to do is I'd like to plot them all out here. This versus this, this versus this, this versus this, etc. Right? So I'm going to insert chart, scatter straight lines, select the data, add, series name, the acetone, X values will be here, and Y values will be here. Okay. Let's see how that looks. So there's the acetone spectrum showing up. And we're going to add ethyl acetate, X values here, and Y values are here. Going to add toluene. And we're going to add the unknown. Like that. So I think we should add a fourth method to this process. And the fourth method should be to determine the relative concentrations by I. There we go. Let's actually go maybe to 340 here. There we go. That should sort of clear things up a little bit. So this is sort of an interesting set of experiments here, because it shows off a number of interesting issues with UV-Vis, and I write off. First of all, you can see that there are the three components here, which are the blue, the red, and the yellow. Right? And then there's the mixture, which is this gray one here. So, no, I'm sorry, the mixture, which is the yellow, and the gray one is the toluene, sorry. So let me add a legend to this guy so we can see what's what here. Just put it up here and make that bigger. So can anybody by inspection tell me what the acetone concentration is in the unknown relative to the acetone concentration in the standard? Kevin?
Is it where they meet, Dr. T? Would it be like 0.75 or something? Or no?
That's a good guess. That's a good guess. So any other guesses?
Is it like the same at like a certain wavelength?
There are wavelengths where these guys cross, right? But like what we're wanting to do is determine for this golden colored spectrum, this is the mixture, how much acetone is in that mixture. So let's talk about the spectra in general here first. First of all, let me add. Let's see here. Design, add, titles. This is wavelength, right? In nanometers. And this is the ununited unit of absorbance, right? And we can see here that below 220 nanometers, three of the four spectra have an unusual looking feature here where they come up and then they flatten out. Right? So this is actually real typical negative deviation from Beer's law. And it happens at a value of 3 because 3 is where the light power is 1/1000th of the blank light power. So what this tells us here, this flattening, is that we have no information at this wavelength. So I think we have to limit this actually to 225 nanometers. So let me say instead of 200, let's go to 225. And let's go to 325 here. There's really not much happening beyond there, right? So the zeros and the values greater than an absorbance of about 2.5, I put them completely aside. Say, no, we don't really care about these data. Now let me modify this value here and make it go from 0, which is the minimum physical value, to 2.5. Okay. So now does this, so now what we see here is there's the toluene. There's the, I'm sorry, this is the ethyl acetate. Toluene, the acetone, and the mixture here, right? Now, one thing that I can say about the acetone and the mixture, right, is that their absorbance is almost the same all the way at wavelengths greater than 275 nanometers, or maybe 280 nanometers, right? That's where they just start to correspond almost perfectly. So what does that mean? Romel, do you know?
Good question. I don't.
Okay. Tina, do you know? No? Not sure. Okay. So if I gave you, so this guy here, this is about 1% acetone. So let me actually change this here and say it's 1% standard. Okay. And ethyl acetate here is I think it's 0.5%, although I could have those reversed. And toluene is 0.05%. Right? So if this blue one, instead of being 1%, if this blue spectrum here, if this standard were not 1%, but it were actually 2%, what would its absorbance spectrum look like?
It's gonna be higher.
Absolutely correct. Absolutely correct. By what factor?
×2.
×2, yeah.
Exactly. Exactly. It'd be exactly twice as high. And so instead of going from 0 to say 0.8 here, it'll go from 0 to like 1.6. It'll be exactly twice as high, right? So now with this information, who can tell me what the concentration of acetone is in the unknown mixture?
Oh, so
Assuming
it's
the
like
unknown.
the mixture, right? Because it's matching the
Sorry?
signal. It would be 1% of the mixture because it's matching the signal of the absorbance.
Exactly right.
So then, like
Yep.
when it's for like toluene, because it's a slightly higher signal, it's a higher concentration.
Is it higher concentration in the unknown or in the standard?
In the unknown.
Higher in the unknown than in the standard. Okay. So, what about ethyl acetate?
Would be lower. I'm assuming it's
Lower
because like
in-
the dominant signal that's being seen at those certain wavelengths is the only one that's kind of being represented on the unknown. So then like ethyl acetate is like the most visible one compared to the other standards. So the ethyl acetate concentration is actually lower in the unknown because it's at a smaller absorbance than ethyl acetate standard.
Exactly right. Okay. Tyler, can you repeat what Kevin just said? Catherine, can you repeat it?
He
Oh,
said,
I see. There you go.
he said the lower the absorbance, and then I forgot.
Okay. Okay. So Tyler says the ethyl acetate is higher in the unknown because the absorbance is stronger in the unknown. Okay. So this guy here, this is the standard, and this is the unknown, right? Tyler? So if we took, for example, wavelength of 230 nanometers, say the absorbance of the standard at 230 is 1.5. And the absorbance of the unknown mixture at 230 is 0.75, almost exactly. What does that mean about the absorbance, about the concentration of ethyl acetate in the unknown relative to the standard? Leo.
It means that the concentration of acetate in the unknown is like about 75% of the concentration in the standard, or whatever the ratio of the
I think it's half.
absorbance of that is.
1.25, and then the ethyl acetate's around like 2.5.
Yeah, so we've got 0.67, and 1.3, something like
Oh,
that.
so that's about 2 times.
Yeah, exactly. Almost exactly 2 times the EA in the standard. Hector, good morning.
Morning.
So, do you believe what we just said?
Yes.
Okay. Let me ask somebody why that's not right. Why is this slightly wrong? We got
Should it be
One
half,
from-
not times 2?
no, that's not the reason. That's a good try. That's a good try. I mean, it's not really the way we're composing the ratio, because C and A are directly proportional, right? Concentration and absorbance are directly proportional. But in this mixture, what 3 components are present in that mixture? Exactly, William, right. There's all 3 in the unknown.
Oh, so like because you're saying you can't directly compare because you're getting signals from all the other ones as well, right? You can only
Right.
compare areas where like ethyl acetate has no signal, or
Right.
in other regions where there's no signal of the other 2 compounds.
Don't worry, I'm not going to say another word. This is your day. I just wanted to say that I'm really glad you're here. I think you're awesome, and I love you.
Well, I'm listening in. I love it. Is that from Kevin?
Sounded like from someone's TV.
Yeah. Okay. So if there's some contribution to the unknown mixture absorbance at this wavelength from acetone and toluene, I'm sorry, from acetone and toluene, and it's not all from ethyl acetate, right? That if we look at this absorption here, say this 0.75, well, we say it could be exactly half of the standard here, but it actually has to be different than that because there's also some acetone and toluene in there, right? So these two components are present at this wavelength as well. So so does that mean So there's basically two possibilities here. That mean either this contribution here means that the mixture concentration of ethyl acetate is either greater than 1/2 or less than 1/2 of the standard. Who can tell me which of those two it is?
Well, can't you kind of like figure out that it has almost the same concentration of toluene, because we figured out the acetone concentration, and then because ethyl acetate doesn't have a signal at like 255 as like the same concentration of toluene, so then you can kind of like I don't know, in those other regions not take into account toluene signal. I don't know.
You're on the right track.
I think the concentration of ethyl acetate in the unknown is gonna be higher than the 1/2 of the standard, because the acetone and toluene has such a low absorbance.
Mhm,
Uh,
mhm.
so it's gonna affect the absorbance of the unknown. It's gonna pull it down. So even though the unknown still have like 1/2 of the
Mhm,
absorbance of
mhm,
the
mhm.
standard ethyl acetate, so the real concentration of ethyl acetate in the unknown is gonna be higher than 1/2 of the standard, I guess.
Excellent, excellent, excellent reasoning. Okay. Completely wrong, but excellent reasoning. I'm sorry, I just wanted to say that. It is excellent reasoning, right? And I want to go over the reasoning here. And Leo, thank you. I really, really appreciate it. I can't help. I want to be a cut up all the time here, but the key difference in what you said was these are small. These contributions are small, right? But they are contributing to this signal at the wavelength where we're making the comparison with ethyl acetate here, right? So, the key was, thank you, Catherine. Yes, it was a good effort. I know that's messed up. I'm just mean.
What you're saying is it's probably less than 1/2 because they're adding to the signal of ethyl acetate in the unknown.
Right. Exactly. Exactly. So Leo was right on the nose, but he said these will pull it down because they're small. But actually they can't pull it down. A component, no matter how small it is, if it's 0, it will make no contribution. And if it's positive, it'll make some positive contribution. But the contribution cannot be negative, yes.
Because like the machine can't tell the difference between the compound, so just when it detects the compound, it just adds the signal, I'm assuming, right?
Well, that's also an interesting thought there. So all the machine knows is what the absorbance is at that wavelength, right?
So those compounds are just contributing to its color regardless.
Exactly. They're contributing to the absorbance at every wavelength.
So they doesn't take the average, they just add up, right?
Exactly.
That's why. Yeah.
Exactly. Okay, so now we have a couple of things here, but of all the, so now let's talk a little bit about one thing that Kevin was saying. So now I'm going to pick on Kevin a little bit, and Catherine, lab is over when it's over. So, no, just kidding. No, probably by 11:15 or so. So, what is let's talk about your conjecture about the toluene concentration in the unknown and in the standard. So now what we're doing is we're looking at the component of this gray standard in the orange one.
It's less than the toluene concentration in the standard because acetone contributes to the absorbance, right?
That's actually true. So, but I wanted you to get it wrong so I could make fun of you.
Oops.
It's actually sort of a tool. It's entertaining for me because I'm a sadistic bastard. But it's also sort of useful as a tool for getting other folks' attention. So why don't you intentionally get it wrong, and then I can berate you, and then get other people to chime in.
Okay, it's the same.
No, you fool! It is not the same. So, so if we want to look at one way to do this, right? You say, well, you know, here's the acetone. The acetone is exactly the same in the standard and the sample, right? Now there's toluene contribution over here, but if we're talking about, say, 250 and above, then we can just subtract out this acetone from this mixture, and the leftover part will be toluene in the mixture. Does that make sense? Let me give it a try here. So there's a mixture. Now let's say, let's make another one. That's the net absorption of the unknown minus the acetone. Okay, so this is going to be the unknown minus acetone. Does that make sense, everybody?
Yes.
Excellent.
Yeah.
So now I'm just going to sacrifice this guy for a moment. Move him over there. Okay. So now we're ignoring the ethyl acetate. So we basically have to think about only sort of this side of things, right? So there's the mixture. There's toluene in the standard, and there's the net toluene in the mixture relative to this, and then we can see what that is relative to the standard here, right? So based on this, who wants to try? Oops. Sue? What is the concentration in the unknown, in the unknown here of toluene? Sorry, here's the unknown, right? What is the concentration of toluene in that unknown? Say relative to this standard. You can start with saying, is it greater than the standard or less than the standard? Less than the standard. Excellent, excellent, excellent. Okay, so it's less than the standard. So the let me make this clear. The concentration of toluene in the mixture is less than the concentration of toluene in the standard. And that comes directly from this relative to this, because these are actually, if we only consider, say, these longer wavelengths here, this and this, they look pretty similar, the orange and the gray here, right? So now, having looked at this a little bit, I want to go back to the lab manual, and I want to see if this makes sense, because this normally gives people some sort of, like, it's like a narcoleptic, you know? It basically puts everybody to sleep immediately, you know? But we'll see if we can stay up for a minute. The absorbance, now we're going to talk about component A, B, and C and the mixture, right? A of lambda is equal to epsilon of lambda times BC of, you know, these are all the A's, right? A sub A, epsilon sub A, and C sub A, right? And these are the standard spectra here, right? Then the mixture has epsilon of A times C sub A in the mixture. So an epsilon B times C sub B in the mixture, and epsilon of C times C sub C in the mixture. So here we have the measured, right? And then epsilon of A is calculated from a measurement here in a known concentration. Epsilon of B is calculated from a measurement here in a known concentration. And epsilon of C is calculated from a measurement here at a known concentration, right? So the absorbance of the mixture at any wavelength is equal to epsilon of its component times the concentration of its component. Okay, so there's really no trick here. Excuse me.
Bless you.
Thank you. Thank you. So So does it make sense to everybody that this is these are, I got the virus. I'm going to spread the virus electronically here. Actually, I sneeze every morning when I eat. Ugh. And now when the sun comes out, I sneeze. Weird. But I could have the virus too, but who knows? So, so I think it's important that you sort of satisfy yourself that that basically these four equations are correct. This is sort of a definition of the standard spectrum, you know. You know, A, the absorbance of lambda, this is just a measured value, right? And you could say that the concentration is also a measured value. And that means that you can calculate epsilon of lambda by taking A and dividing by B and C. Catherine writes, can you give us an example of how to figure it out? Yes, yes, I'm getting there. Thank you. So, so when you have the mixture in the standard spectrum, there's a few ways to proceed. And probably the one that'll make most sense to you is 3 equations and 3 unknowns. Right? If we choose lambda 1, lambda 2, and lambda 3, just choose 3 wavelengths, right? Then we can write 3 equations. Absorbance of the mixture is equal to epsilon of acetone at that wavelength times B times C of acetone. Here, in this case, this is known, B is always 1. The unknown is C, right? CA, CB, and CC, right? And how do we know epsilon? Well, the way we get epsilon is we take the standard spectrum and we divide it out. Let me show you how to do that. So let us just say here, actually, I'm going to go ahead and get rid of this guy because I don't want him anymore. I want ethyl acetate back. So now what I'm going to say is I'm going to say epsilon acetone, epsilon EA, and epsilon toluene. Okay. So in order to calculate these, what we need is the absorbance and the concentration. So the concentration of these guys, we're going to get from, oops, this is the wrong one. Concentration for the standards. Concentration for the standards is going to be 1% for acetone, 0.5 and 0.05. So this is at 1%, right? So epsilon is going to equal absorbance divided by 0.01. or 1%. That's actually, let's divide it by this.
You have to divide by B because B is always just 1 centimeter, right?
Right, exactly. Okay, and ethyl acetate is 0.005. Wait, sorry. And toluene is 1/10 of that. So we can actually acetone, ethyl acetate, toluene. There we go. So now I'm going to double click here. Now these are the extinction spectra. So these are just copies of the absorbance spectra, but they're scaled to reflect the absorbance of a unit concentration of, say, for example, for neat toluene or whatever at this path length. Although it's not, we're never going to actually observe that, right? Because that's too large of an absorbance value. So, what we're going to have to do is we're going to have to choose a few wavelengths, choose 3 wavelengths where we're going to figure this out. And I suggest that we do it in an intuitive way. Okay, so Tyler's asking about the negative epsilons, and the negative value in epsilon is from a very small negative absorbance here. And that's non-physical, but it's because it's out around it's in the tail of this around 400, and the absorbance is oscillating between plus and minus 0, basically. It's, plus or minus 0.05 around 0 here. So that's the meaning of these negative values here. So hold on.
That's instrumental fluctuation is what's causing the negative values?
Yes, exactly. Yes. Yep. So, so in order to calculate these concentrations, we need to choose a wavelength where we can do this analysis. So, let me just, well, let's just choose them right away here. So I would say, I would choose as one value 285 nanometers. Right? What is true about the absorbance at 285 for the mixture?
It's only acetone?
Exactly. Exactly. The only contributor at 285 is acetone. The toluene and the ethyl acetate are around 0. So this is also hopefully can help answer Tyler's question about the negative value. And that is normally we can ignore the negative absorbances and epsilons, unless they're coming about because the absorbance has gotten so high that it blows up. But normally we can ignore it, and you'll see when we get to it. We're going to do a couple tricks. Okay. So let's use 285. And when we measure 285, right, we're going to have A at 285 is equal to epsilon for acetone at 285 times concentration of acetone in the mixture, right? Plus, and then what we're going to do is we're going to have that plus B, right? That should be A, capital A there, right? And then we'll have C. So we have these three contributions at 285, right? Epsilon A, Ca, epsilon B, Cb, epsilon C, and Cc, right? But what I'm going to offer here is that epsilon B is 0, and epsilon C is 0 at 285 nanometers, right? So A at 285 is equal to 0 plus, it's equal to this plus 0 plus 0. Because at 285B, which I'm using for toluene, is 0, and C for ethyl acetate is also 0. Tina, does that make sense? Yay! Romel, does that make sense? Yay! Hector?
Yes.
Yay! Leo?
Yeah.
Kai? Kai just got here, I think. Sue? Yay! Tyler, I think that makes sense to you, yeah? Kenya? Catherine? No. Okay. So we got to get Catherine on board here. At 285, it's all acetone, right? The only contributor to the signal is acetone. Okay, all right. We can talk about it later. All right. So so we can get, so if we know the absorbance, we know the epsilon, we can calculate C, right? Calculate the concentration of C in the mixture, right? Then what we can do is we can come out here to this wavelength, the 267 here, right? And we can use that wavelength, and we can set up this same set of equations, except replace 285 with 267.
And that's because we know at that point we should know acetone's concentration, and then there's no contribution from ethyl acetate.
Exactamundo. Kevin will be available to sell that information on eBay. Okay. So the next steps here is solve for CaCAM, right? Ah, it's defeating me. Oops. Okay. So now at 267, we know epsilon. Oops. We know the absorbance of the mixture. We know epsilon of, we know all the epsilons. And now we know concentration of A in the mixture, right? So the only unknown is concentration of B, because we know the epsilon C is 0. So in this case, we know A, Ca, epsilon B, Cb we don't know, and then the last term is 0. So here we solve for Cbm, right? And then lastly, we have to put in a value, say at 235 or something like that, or 220, or 230 rather. And then let's say A 230, oops. Epsilon A at 230, CAM plus, oops, epsilon B at 230, CBM plus epsilon C 230 C. Okay. So what we need to know now is of these variables, or of these symbols here, what are the knowns and what are the unknowns? So absorbance of 230, do we know that? Absorbance of the mixture at 230, so it's actually should say A sub M at 230, but yeah. So there's the mixture at 230. So we know absorbance at 230, right? How about epsilon of A at 230 nanometers? Do we know that? Kai, do we know that? Tina, do we know epsilon of A at 230? No, epsilon of A at 230, right? There's epsilon of A. We just come down here to 230, right? Oops. There it is. And it's 1.81173. Okay, good. How about concentration of A in the mixture? Do we know that? Kenya.
We get it from solving the very first one. The
Exactly. Yes. Exactly. It's the orange numbers. No. And sorry, I was reading your comment. Yeah, we do know epsilon of A, and we know C sub A, right? And C sub A is a single value, and we got it up here, right? And we know C sub A is actually 1%, right? Yeah. Yep. And Kevin says, so you just plug in all those epsilons at that wavelength and solve for concentration of C. Exactly. So you got a A of 230 is unitless. Epsilon C is unitless. Epsilon C is unitless. And then you've got epsilon of component C times C component C. And this is reciprocal molar, and that's per percent, and that's percent. So you can solve for CC in the mixture. Does that make sense? Alrighty, kids. I think that's probably good for today. Why don't you see? I still have to throw these up onto Canvas, but I will throw all the data onto Canvas, and then I will I'll let you work through it, kind of like I've done here. And to do this, this is called selective elimination, and we can go through it in that way. And then next week we'll do the LinEst form of this. Are we okay? Yeehaw! Excellent.
When is your office hour? Did you record this?
It says recording, and if it shows up, I will post it.
Okay, and you're gonna post your office hour too?
My Zoom office hours, yes.
Okay, bye.
All righty. Thank you. Thank you so much. Thank you. Okay, everybody. I will see you Thursday or sooner. Bye.